Today you're going to be learning about the terms static electricity, Coulomb's law, and how that uh, combines with conduction and induction. We're also going to be learning about how static electricity works and how conduction works, induction, and also how lightning. So we're going to start off with static electricity. So static electricity is that is when electrical charge that is built up on a surface or a material and is static, non-moving. So static electricity, there's two kinds of charges, negatively charged and positive charges, and you can charge two objects by two different means. Charging by conduction or charging by friction, same thing, or charging by induction. So if you have at home, you could actually do this. If you have a plastic ruler, you can take a wool sweater, or even if you have long hair, you can do it with hair, depending on if you have conditioner or not. If you don't have conditioner in your hair, long hair, you can wipe it down with your hair, kind of like you do with a balloon, or a woolen sweater works too, and you can pick up little pieces of this. Now, the ruler carries electrical charge. You are wiping off electrons onto that little uh, plastic ruler, and that's going to exert an electrical force on the paper. Now, this is called charging by conduction. You are touching the pieces of the ruler to your hair, forcing the electrons to rub off onto that ruler. Now, the rubbing material does not create electrical charge, it just transfers the electrons from one material to the other. So you can do this again with a balloon, and you can rub it on a woolen sweater or your hair, and you are grabbing the electrons from your hair or from the sweater and putting them onto the surface of the balloon. So overall, the balloon becomes negatively charged, but your sweater becomes slightly positive. So you cannot create nor destroy charge. Now, insulators are materials that do not allow electrons to flow through them easily. So insulators like rubber, glass, air can easily be charged by friction due to the fact they can't easily escape. They can't just transmit right through the material. Unlike conductors, which allow the electrons just to travel anywhere they want and leave the material, if you have a rubber balloon, it stays on the surface of the rubber balloon. It will not transfer all the way to your hand and back down your arm. So conductors allow electrons to flow more easily. So they, again, cannot be charged by frictions. So you can't get a metal surface to conduct very easily. You can't rub a metal ruler on your hair and get it to get a static electricity charge. Only the rubber balloons can do that. Now, the second way of charging something is by induction. This is when you get something close to it, but not touching it. So we have this negatively charged electrons. You might not be able to see it here, but there's little negative electrons on here on this rod. So this is just like that little ruler we had earlier. It gets close to a metal can. Now that metal can is going to attract the positive charges up to the top. The negative charges are going to be pushed to the bottom. And now these are inducing a charge. You're causing the top of the can to become more positive and the bottom of the can become more negative. And so the top is going to attract, the bottom is going to repel. Small pieces of paper. You can do the same thing. All the positives are being pulled up, negatives are being pulled down, and there's going to be attraction. And if you do this with a small enough piece of paper and a strong enough ruler that's been charged enough, you can get the paper to start kind of standing on end on one side, will be attracted, while the other is going to be kind of pushed down, and you can make that little piece of paper to dance. Styrofoam peanuts are also great at doing this. Now, static electricity, on the other hand, is when your body builds up enough electrons, they finally discharge, they jump to the nearest place that can get rid of them. Usually the ground. The earth has a lot of, it can absorb a lot of electrons or give up a lot of electrons very easily. Now, our body cannot feel more than 2,000 volts of electricity, but yet scuffing your shoes can exceed up to 20,000 volts. Now, to give you an idea, the wall electricity out of your wall socket is 120 volts. So everybody's like, wait, what? Those don't make sense. I will tell you that voltage has nothing to do with lethality of electricity. Okay? So lethality of electricity deals with what we call current, which we're going to go into later. Voltage has nothing to do with that. It's related, but it's not a direct relationship. So a balloon has a negative charge when rubbed by a woolen cloth. If the balloon can attract some paper scraps, which of the following cannot be true about the paper? They're negative, neutral, or positive. So if you said that if they are negatively charged and they're attracted, they could either be conducted. By induction, they can be attracted, or they could be positive and attract to the negative charge, but they cannot be negatively charged. So if a balloon has a negative charge when rubbed by a woolen cloth, during the rubbing, what happens to the transfer between the woolen cloth and the balloons? Well, electrons are being transferred. You can't transfer the protons because that's what makes up the material, and you can't transfer neutrons because that's just weird. So, again, when a positively charged rod is put near a neutral object, the negative charges are induced or pushed to the side near the rod. Positive charges are induced to the side away from the rod, and the rod can then attract a neutral object because of attraction between the rod and its negatively induced charges and repulsed by the positive charges. So that was just kind of a summary of how induction works, like in words. So then what is grounding? Well, grounding is when you touch the object to the earth and excess electrons can move either to the object or away from it and it becomes neutral. So how does grounding work? Well, the electrons can come from the earth and dump into this positively charged metal ball, or if it's the other way around, the negatively charged electrons will travel through the finger down into the earth. Your house has a neutral. That's what actually is on the bottom of your light socket. When you have when you plug something in, there's that third prong. One side's positive, the other side's negative. There you have what is called ground, which is that round little one. That is to deposit any extra electrons that might build up accidentally in your electrical device without frying it. They will dump it through that ground, so it's a safety measure so that you don't burn down your house. So why do gasoline tankers usually have metal chains on their back? Well, as you're driving, you have your rubber tires only touching the ground. They're good insulators. And so the friction of the air friction coming across the body of the semi is going to build up some friction, static electricity. And for gasoline tankers, if you can, large enough, you can actually get a spark. And that can then induce an explosion. Bad things happen when that happens. So they put metal chains on the ground, so every so often, if it hits a really big bump, those chains slam down into the asphalt, discharge, and that avoids any danger. Now, lightning. Lightning is just a static electricity spark that happens with nature. It's literally the same thing as putting on a pair of woolen socks and running around your shag carpet and zapping your little sister on the nose. Same thing, it's just a lot bigger. Lightning has killed more than 60 people a year, injuring 400 people. It happens every mile, every 5 every mile, every 5 seconds, and its temperature can exceed up to 5,000 degrees or 20,000 degrees Celsius, and voltages up to 120 million volts. It's ridiculous. Or 120,000, sorry. Now, how it happens is the clouds rub against each other or in the air itself and get excess electrons or remove their excess electrons. So one part of the cloud becomes positively charged, the other becomes negatively charged, and they can either jump, the electrons can jump from one cloud to another, and we call that the intercloud strike, so that's cloud to cloud, or it can come from the cloud down, dumping those extra electrons into the earth, and that's when you get that cloud to ground lightning strike. So here's some pictures of that lightning happening. So when lightning happens, it's going to send out little feelers. That's these little tendrils. And because air is a very good insulator, it's going to try to go through it. And once it finds a really good, the shortest path to the ground, such as, let's say, a lightning rod or a tower or a human body, then it's going to dump all those electrons down simultaneously in one big flash, and that's what we get that lightning. Now, thunder is just when you heat up the air, because remember, it's 20,000 degrees Celsius. You heated that air from being fairly cool to 20,000 degrees, and that's going to expand that air really rapidly, and that's going to increase that thunder, so that shock wave. So, what happens when a golf course gets hit by lightning? Well, you get these really cool little fractal patterns going on, these little striations. Also, when lightning strikes sand, sorry, Sweet Home Alabama, it does not turn into clear glass, but it does fuse the sand together and creates this. If it hits a human, you get the awesome scars and probably some really, if you're lucky to survive it, quite extensive burns, but you get really cool tattoos afterwards. But these are the lightning burns that went through this person's body. So these are two different individuals. The reason that this person was able to live is because it didn't go through their heart. If lightning strikes through the heart or the brain, then it can actually cause lethal level of it can cause a lethal dose of electricity and stop your heart or brain function. Now, if it traveled through, in some of those gentlemen, it looked like it traveled through their arm and from their shoulder to their arm, you're perfectly safe, except for the fact that they probably got extensive burns. So, what affects levels of current? Well, we said that current is what kills, not voltage. So 1 milliamp, slight tingling sensation. 2 to 9 is a small shock. That's kind of like your toy cars, or the toys that shock you. Those are that kind of level. 10 to 24, muscle contraction causing you to freeze. A lot of athletics will use these to cause your muscles to contract and release, and that's this level. 25 to 74, you can have respiratory damage and paralysis, may cause pain and even get burns. Tasers are going to be right in between this. They're going to be kind of on the 24. They want to constrict all the muscles in your body, but not your respiratory muscles. If you get 75 to 300, usually this is going to be lethal because it's going to fry your heart, cause ventricular fibrillation, also known as a heart attack. And you can actually blow open your exit wounds, causing visible damage. And above 300, almost death is certain. Because you just fried your body, it literally burns you, and you'll have massive burn damage. So, if you guys want to see any movies, look up Tesla Coil. There's great videos on Tesla Coil, fun videos about Tesla coils shooting off electricity, and we have a Tesla Coil this classroom if you missed that demonstration. Also the Van de Graaff as well, if you want to look up those videos. Those are awesome and great fun. So, if you have any other further questions, please go ahead and ask your teacher.